So ternary structures and ternary categories. I could be talking about n-ary stuff for some of the issues that I'm going to be discussing, but I really want to focus on n equals 3 for several reasons that will be apparent by the end of the talk, hopefully, but mostly because it's the sort of nearest step from binary, which is what we all know and love. So I should say, as a disclaimer, this is very much work in progress. I've not seriously tackled any of the things that seem to open up, any of the sort of research paths that seem to open up. And actually, my motivation to present this topic here was precisely to get some inspiration, to get some attacks and criticism for my line of thinking. So in that vein, let me begin with some philosophical and notational remarks that sort of motivate my ideas. So the first thing I want to reflect upon is, so let me just bring this first, start with assuming. The first thing I want to bring to your attention is the strongly binary flavor of modern mathematics. So of course, the vast majority of algebra is concerned with binary algebraic structures, groups, rings, modules. At the core, they're mostly made from binary operations. Indeed, arithmetic is built from the sort of binary operations. Then, of course, categories. I mean, we are in the categorical lunch, so categories, which abstract maps, relations, homomorphisms, etc., are naturally very binary objects, or very binary structures. And then, of course, logic, propositional logic, and fundamental logic that runs through mathematics, and in some versions of foundations of math is the foundation of math, is indeed binary. I mean, in terms of truth values, and then truth tables have this sort of binary structure to them. So this is just something that everyone, I think, agrees on. But then I want to also go a little bit meta-mathematical here, and a bit perhaps even sociological, when noticing that we use a very ubiquitous linear notation. So mathematical notation for the majority of history, of recent mathematical history, has been linear. And by linear, I mean these kind of examples, a plus b, a plus ab, x, y, z, this sort of n-tuple notation, and so on. So I would say that probably this has a strong influence from the fact that notations come mostly from European languages, and say versus something like the Chinese kanji or more Asian influence languages that have more sort of spatial distribution of symbols, not just linear. And I would say that this has been, although it was at first perhaps directly influenced by the languages that the mathematicians were using or the scientists were using, I would say that this was constrained further by the printing technology that really requires sort of this linear placing of symbols and characters. So of course this is until recently, right? I mean, now we have our wonderful rendering programs, and we can do all kinds of beautiful things, even in 3D with virtual reality. This is all well and good, and one could just set out to try to go beyond binary by going ternary into categories, but actually I have two problems in mind that are quite concrete, and I think should be, out of all mathematical merit, and they have no philosophical flavor to them. So I want to present them to you. One is slightly less somehow deep or fundamental, and the other is actually, in my opinion, quite a big problem in Lie algebra theory. So the first one is cubic matrices. So cubic matrices have been discussed in some capacity since the inception of matrices, essentially in the 19th century. But here are some references that show sort of the current understanding of these things. So it's quite recent. I mean, there's a small but industrious group of people working on cubic matrices and ternary algebras in this vein, and they all work with cubic matrices in the following sense. So let me just introduce the characters of the play here. So we have some set of indices as usual, like in square matrices, and some field, could be the reals, could be the complex numbers. And so a cubic matrix is just this 3-index array of scalars, so to speak, of numbers. And the interesting thing is that there are several generalizations of matrix multiplication. So first we have a binary multiplication, in fact, several binary multiplications, which are associative, actually. And they basically have this same feature with a square matrix multiplication of contracting two indices, right? You can see in that formula that ijk is indeed the sort of the three free indices, and then you're contracting the third and second index. So there are more possibilities in principle, but that's certainly the sort of the type of binary product that you can define, and they are in fact associative. But then most interestingly, you have also ternary products that you can define in analogy with usual matrix multiplication. And I wrote down two of them. It might be that these are the only proper ternary products, as we will see later on. But these are certainly ternary products that you can define. And as you can see, the sort of the summation pattern of the indices, it just sort of generalizes in some sense the usual matrix multiplication. These are non-associative products, and by associative I mean three associatives. So this is word associativity, so that you can bracket things in a linear way. And so this is going to be a theme of my presentation, that this might be not so much the proper way to think about it, or the most effective way to think about these things. So in the existing literature, it is very common to find that cubic matrices are Macy's expressions for tensors, right? Three index object, especially in the more sort of physical literature. It is very, very common that for some VAF vector space, A, I, J, K will be the components of some tensor. And often they don't really specify what order the tensor is. So they don't specify the contravariant and covariant orders. So they just say, A in V tensor V, and call it a day. And this is a problem, actually. It is a problem because if you say that A is in V tensor V, you know exactly how it transforms with changer basis. So this is a proper sort of intrinsic linear object. However, as I write down here, I say covariant and contravariant indices cannot be contracted or traced out, if you use that language, consistently, so that the ternary products are internal operations. So what I mean is that it's just a fact of combinatorics that tensors have, without any extra structure, covariant and contravariant indices. So upper indices and lower indices. There is no way to contract sort of pairwise in this sense, so that you will get three tensors of the same kind ternary multiplied into a tensor of the same kind. It's just impossible. So when in the literature they say these things belong to these tensor spaces, I mean, actually there's no canonical way to assign it to one of them, and even if you do, then you have to make sense of all these ternary products in complicated ways. So the best thing you can do perhaps is to say you have some maps, some products from different spaces into different spaces. So certainly nothing looking anywhere near canonical. And so the more profound question that I can pose at this point, let me zoom out a little bit, because I do need to go for the full stretch. Okay, is that if square matrices are the basic expression of linear maps, where are the linear objects associated with cubic matrices? I think this is a very natural question that we could ask. So this is actually unknown. You want to find it in the literature at least. I did my best to find references for this. I couldn't find a source that would tell me what a cubic matrix was the basis expression of, essentially. Okay, so this is one problem. You might think, okay, this is just nice, entertaining mathematics. There's nothing serious going on, and I would agree with you at this stage. But actually, there is a much more important problem that revolves around 3 Lie algebras. So the main reference I would point you towards is Azcárragas and Izquierdo's review from 2010. And I would say that the field of 3 Lie algebras and NRE Lie algebras has stayed more or less the same in the last 10 years, not many developments. So what is a 3 Lie algebra? So as you might expect, is the direct generalization of Lie algebra. So you have a vector space, you have multilinear multiplication that is fully antisymmetric, and you impose the sort of the Jacobi identity for these objects. So the way to read this formula looks very long. It's actually just a direct generalization of the fact that Lie algebra elements should act as bracket derivations with the bracket, right? This is essentially what all it's saying. So in this case, x, y, blank would be a derivation of this ternary Lie algebra. Okay, so there's a very natural example of this, actually. So the cross product in R4, so cross product here, I mean not the metric cross product that only exists in R3 and R7, which is very closely connected to the division algebras business. This is the cross product that directly generalizes in terms of finding, sort of building the parallelopipeds and so on, sort of the parallelograms, parallelopipeds, etc. Right. So this idea that you can complete the codimension one sort of shape, right, in space. So there you have the formula. It's a direct generalization of the usual, linear algebra formula, and you can just check that it actually satisfies that property. No problem. So here R4 with delta. Delta means the Euclidean dot product. So that there's this sense. So very natural question. What is the global object that integrates a ternary Lie algebra, right? And again, this can be stated the same way for n-ary Lie algebras, but I really want to focus on the ternary here. So again, anything that is in quotation marks really needs to go in quotation marks, because I don't think anyone has a real idea of what these things look like. So as you can read from that paper, and I couldn't find any more progress to date, this is an open problem, and it's open in several ways. It's open because we have failed to recover some general construction that would produce ternary Lie algebras or 3 Lie algebras, and so there's some work that has been done, and in some cases it is known that there are some sort of set 3 graded groups that can have some relation, and there's some work done, and in fact n-ary Lie algebras are quite well studied. The theory of ternary Lie algebras in particular is quite well known. But the kind of object that will integrate these algebras is in fact unknown. So there is no good notion of ternary Lie group at this point. And so this is actually my main motivating problem. This was what I was discussing with Jose a few months ago, and I started to get curious. This was very far away, removed from my main research in some sense, which is more in sort of Poisson geometry and Jacobi geometry. But I got very curious about this question. I thought it's such a basic question to ask that it seemed to me surprising that not even the kind of answer was explored. I mean, obviously finding the answer would be amazing, but the kind of answer or how an answer would look like is not even that well explored in the literature. So this is my motivation. Okay, so after fiddling around a lot with trying to define some axioms for ternary like or ternary group like structures, I found myself pretty much lost in the possibilities. And so by the way, there is quite a lot of work on 3 groups, and 3 groups being ternary structures that are associative in the sense of 3 associative, meaning that you can group brackets in this linear notation in the obvious way. And it's well understood that the sort of the natural generalization of group in the ternary case actually reduces to a double product of binary associative operations. So essentially, 3 groups do not go beyond ordinary groups in some sense. And
Carlos, can I ask a question?
Yes, please.
Sorry, you say associative in the obvious way. Just for dumb people like me, could you
sorry.
write
Yes,
down
of
what
course.
that means exactly?
Of course, sorry. Yeah, my bad. Absolutely. I should write that down. So associativity. So 3 associativity will be the following. So essentially, it's so that you can write words, right? So the idea is that if you have a triple product ABC written in this way, associativity will be if you add DE. So now you have 3 elements. One of them is a bracket of 3 elements. This should be equal to A, B, C, D, E equals A, B, C, D, E, right? This will be 3 associativity, and sometimes people just refer to this as associativity. Okay, so I would say that this property is very much sort of biased to the linear notation that we use. It's a perfectly good property. There's nothing wrong with it, but I think it's very strongly influenced by this linear notation that we're using. And this is the kind of property that people were quick to demand from ternary structures. And so when defining three groups, they demand this property. And the basic results, there's easy literature to find out there about this, is that when you try to find the notion of inverse, the notion of identity, and so on in this three group setting, you actually very quickly reduce to the case of binary groups. And so your ternary structure is just the double product of a binary structure, right? I mean, anytime you have a binary structure, you can just apply it twice and you have a ternary structure. So that's what happens there. So anyway, so I started really trying to come up with new axioms for these ternary structures, and I did come up with some axioms that are interesting in their own right, and they sort of show up again, and as I will mention later. But I found myself really lost in this realm of ternariness and sort of this world of trios and where things were non-binary. So really, I got to the point where I thought, categories, so my usual mathematical thinking, I mean, as a working mathematician, I really use categories as my sort of infrastructure for most of my thinking. And I was noticing that categories were very fundamentally binary. And so so I set out to, when all hope was lost and I was not making any more progress on this more direct problem of finding the ternary Lie group definition, I gave up and said, okay, let's just think of what categories can do for me in this more generalized sense. So I went on the literature expecting a very direct sort of neat presentation, even in NLabCat or whatever. This place is just finding a neat presentation of ternary categories, and I just couldn't find it. So there is some literature from Dobenskarov, as you can see here, is in French, however, it's quite obscure, and who did do some work on n-ary categories and n-ary relations in general, but it's quite a brute force approach. So that first paper there really goes brute force and just tries to generalize very widely. And then there is Bass, who's done these higher structures and is really advocating for sort of like more general objects than categories. So let me just emphasize why this is limited in some sense. So n categories, higher categories, and polycategories, I summarized in those two diagrams. I mean, they do have this generalized sense of doing more than ordinary categories, but of course, they are still somehow fundamentally binary. I mean, morphisms are arrows at the end of the day, right? So this is the sort of the pictorial side of this fact. And so the point here is, can we define categories with fundamentally ternary morphisms? So this is the kind of question I've been thinking about for the last few weeks, and this is why I say this is very much work in progress, because for the majority of the time I have worked on this question, I was really trying to find axioms for ternary structures, very sort of algebraic approach, and just try to do geometry by putting some smooth structure on them and so on, because I really wanted to go about this integration problem for the ternary groups, right? So this is the basic question. Can we find such categories? And so with the majority of my talk, I want it to be about some models for inspiration. So in some sense, the template for categories that at least I myself usually think of in the binary case, I want to generalize to the ternary case and see what we can do. So let me check the time. So it's 22 past. So I think I would take until 22 or something like that. It should be only 20 more minutes. So now this is sort of the more mathematical content of my talk. Up to this point, I was just motivating why should I be looking at a ternary notion of category, and I'll be very happy to discuss afterwards. I don't want the talk to be very long. In fact, there's no sort of technical details in the talk. It's just sort of a presentation. So let me run you with this inspiration. So this is really what I've been thinking about for the last few weeks, and I wanted to communicate what the situation is. So on the blackboard right now is basically my two main sources of inspiration of what ternary category should look like. So let me first run with the simplex analogy. So in the simplex analogy, we think of objects exactly the same way as we think in binary categories. So A, B, C, some sort of point-like or zero simplex elements, and then binary morphisms will be one simplicity, so it will be arrows between these objects. And then very directly, we can just say, well, ternary morphisms will be two simplicities, right? So these will be triangles between the objects that are oriented. So I'm gonna use this notation. Perhaps I can zoom in so you can see a bit better. This is temporary notation. I'm not final on this one, but just sort of like the triangle version of an arrow is this sort of like triangle with partial arrows. I don't know. I mean, it can be whatever. But I hope it's clear what it means. It's an oriented triangle between the elements. Now, on the other side, so when thinking of, I mean, the main model for categories, of course, are maps and relations, and of course, maps are just particular cases of relations. So, so I was really thinking, okay, binary categories could be thought of as being modeled after binary relations in some sense, in sets. So if you think of sets, A, B, C, X, etc., as objects of the set category in the usual sense, binary relations would just be subsets of the Cartesian product, and then ternary relations, very directly, will be subsets of the triple Cartesian product. So no surprises there. This is very straightforward. And so I just introduced, again, this triangular notation that is really exploiting the fact that we have a piece of paper or a two-dimensional surface to write on. And so I'm expanding my notations in the plane. So all the notation can be projected down to conventional linear notation, but it's really more compact and really helpful to keep them that way. So I hope that little note here clarifies the notation for the rest of my talk. I'm just going to use that sort of triangular notation. It really just is as you can imagine, this is the natural generalization of this notation, right? So to say that in here, if AB is in R, then we write that A, R, B, right? So it's that kind of generalization. Okay, so now, what kind of structure do we have here? So now we've identified objects and are candidates for morphisms, and so we should think of how do they compose. I mean, in these models for inspiration, we're not axiomatically defining ternary categories. We're trying to find the would-be structure of a ternary category in this particular example. So let's see. So in the simplex side, I just want to depict. So this is more of a sort of intuitive way to regard things. So basically, the idea is, how can we make triangles, oriented triangles, from oriented triangles, in the sense that their vertices will have to be fixed at common objects, right? This is sort of the exact same idea as with categories. So in fact, I'm going to give myself some room here to give you the sort of the analogy. So in a binary category, of course, we have A, we have B, we have C. And so the idea that we can compose is that, you know, pictorially or geometrically, if you like, this is an arrow, right? It looks like an overall arrow. So anyway, this is sort of the inspiration for this. So taking two triangles and putting them together so that they give a new triangle, right? Now, I can do several things with triangles. With arrows, really, we only have one way to do this. But with triangles, we have more than one way to do this. So in particular, we can do a binary composition. So we can fit two triangles like in that picture, and then we will get two possibilities. So we can basically collapse the y or collapse the x, and then we'll get two new triangles. And then we have two ternary compositions. And these are the kind of diagrams that we're getting, right? So again, with the idea that morphisms are triangles that are based on fixed objects, and some of them are in common. And so the kind of intuition that I'm developing about when thinking about these objects is that a morphism ABC, in the same way that a morphism in the general, in the ordinary case of categories, can be thought of as something that has a beginning and an end. So it's somehow like a traveling, the concept of traveling, right, or transition from A to B, a process or something like that. I'm thinking of this ternary relation more of as a flux, right? So it's something needs to be. It's like when you close a circuit, an electrical circuit. Then it snaps, and then something is flowing. And so you can see that if you think that something is circulating from A to B to X, from B to C to X, and so on, you could sort of follow this current and travel from A to B from B to C, sorry, from A to B to C, and then back to A, so that you're going in this cyclic direction, right? So the idea is that things are flowing without a beginning or an end in principle, right? It's just that they are ordered in this way. So this is quite vague at this point. I mean, there, as you will see when we define as I will tell you in a second, the composition of relations, there's actually a lot of freedom on how to do things. But this is sort of the simplex inspiration for that. Okay, so let's have a look at how these operations look in terms of relations, of ternary relations. So the binary compositions are quite obvious. So we also have two canonical ones. So we have X and Y in common, and so we can choose into different ways. So in some sense, these logical formulas are essentially sort of playing with the diagrams. And so, of course, we have two ternary compositions. So we have one in which there is one common set X. So this, again, these logical formulas do really imply the sort of the situation that is reflected in the diagram. So X is a common set for A, B, and C for the relations 1, 2, and 3, and so we can define that particular formula. And similarly, for the for those of you who know the Legend of Zelda video games, this is the Triforce like symbol. We have this other formula. There might be more, and in fact, you can think of some cases of altered indices, but I think the canonical ones that don't assume anything else are these ones. And in fact, these two compositions, the ternary compositions, are identified in the paper from '88 that I mentioned on Ternary Categories. So they are actually identified. Okay, so at this point, one could ask, okay, so I already have, so I have some notions of composition. So now this looks much richer. If anything, it looks much richer than binary categories, because there seems to be different ways to compose these triangles. Of course, I mean, we can do ternary and then binary and then combine them, and it looks like a mess at first. So the idea would be, can we find something like identities? And so to tell you how I'm thinking about identities in this context is, so how do I think of a binary identity in an ordinary category? So I think of it in this way. If I have a morphism of this form, I think of identities as arrows that when I duplicate an object, right? For example, A, I can add an arrow, and this will in fact not change the information I had before, right? So it's this idea that I duplicate one of the objects in a composition, and sorry, in a morphism, and then composition works in such a way that the identity doesn't change the morphism, right? So actually, we can think we can think in this same vein for a ternary composition, and so the basic object now is, or the basic entity now is this ternary morphism. Is oriented like this, and so the idea is, what happens if I duplicate, say, A, right? The analog of identity would be that there is a triangle here. So the picture is going to get a bit awkward, but I hope it's clear. That there are triangles like this, for example, that compose. Now, notice that this has the condition for example, the ternary composition here, that compose in such a way that this actually gives, so all the orientations need to match. So this goes like this goes like this. Whoops, nope. It goes like that, and then this goes like this, goes like this, and goes like that. Not again, like that. So you can compose this in the same way as we had before, the triangle composition, and this should be, again, back to ABC. The question is, can we assign that canonically, right? And the answer is yes. The answer is, well, we can see it in the context of relations to see it more explicitly. So let me define what an identity is. So basically, identities in this context of relations are partial diagonals, right? So let me just define. Given AB, So again, similar to what we had before, in that you give me one object, and then I can immediately sort of duplicate and create an arrow from the object to itself with some nice compatibility conditions. Now you give me two objects instead of one object, and I will always be able to find a triangle which has this duplicate object. And so this is, let me actually make the diagram bigger so I can fit my notation inside. So I'm going to call this AAB1, right? So let me just write it here. So in analogy with, one sub B for identity, I mean, again, this notation is quite temporary. I don't think it would be particularly useful, but it's very simple to define this. So this would be a subset of A times B. So I just define this to be a partial diagonal for A in A and B in B, right? So yes, you can check, in fact, that some nice properties happen with these partial identities. So of course, you have the full diagonal when you do AAA, and these full diagonals do play interesting roles, of course. But for example, some nice formula that you can check quite easily is that given a morphism T, you can find T triangle 1 A B and 1. Now it should be so of course. So let me be clear. So if you have a morphism ABC called T, right? Then if we have this kind of situation where we add these two identities on the left, then the composition symbol here will be, so 1, and then we'll have, the order might be swapped, but this is the essential. So 2 A's and 1 B, and then 2 A's and 1 C, and then in here you'll have T that has A, B, C, right? And so you can actually check that with the definition above, this is in fact T. So it's very nice. So, and you can check other formulas for the identity. Now, what about associativity? So we have half of the definition of a category. We have the axiom of identities. Now we have direct inspiration of what they should like and probably what the axioms should look like for identities. But what about associativity? And so this is essentially the question that I've been stuck with for a long time, and I couldn't find clear answers anywhere. And I hope that very, very intelligent and knowledgeable people in this seminar will give me some ideas, or at least point me to some interesting literature, because I really have no good intuitions of what these things should look like and what I should be looking for. So the things that we do know, and there are quite simple consequences of the definition so far, is that the two binary compositions are in fact associative. So with each other among themselves, right? Like for each of them are just two associative, and these things are two associative, and the identities act as identities. I mean, you know what I mean. So basically, when you compose identities, you get this. So what's the idea here? Well, the idea is that you can imagine having some common object X and then a string of objects like this. And so what's happening here is that you have triangles like this, etc. And so basically they compose in the obvious way. So you can always add an identity here, for example, right? And so double A with X, that's the identity 1, and so that will do nothing, and so on. So you basically recover associativity, you recover binariness in this ternary world in this way, in quite a direct manner with this ternary relations. But of course, what's with the triangle and the three-fourths compositions? So these two compositions do not satisfy. So these are not three associative. If you collapse the notation back to linear notation, they are not three associative. So I don't need a bracket now, sorry. So these are not 3 associative. And it turns out that there's another axiom that I've called associativity, which is notationally inspired by associativity, but in this triangle notation, that actually seems a lot more plausible. And by a lot more plausible, I mean that when you look at the logical formulas, there's no possibility for 3 associativity to work. I mean, it just will never work. Will have to be some very degenerate and trivial cases where it might work, but there's really no hope to work. And again, the analogy with cubic matrices highlights this fact a lot. But when you look at the logical formulas, actually, the kind of axioms that these things almost satisfy, and by assuming some like duplicated objects or something like that do satisfy, looks like associative. So they are not associative, so it's far from associative. Far from associative, but are only not quite associative. So let me write down the axiom. So what is my notation? So well, the notation, again, I'm going to try and exploit the sort of the planar nature of my writing space, and so instead of using binary brackets, so binary notation, you would write things like this, right? Or a ternary product, you would write it like this. So now, because you're in a line, so you just need to specify the brackets in what parts of the line you find yourself. Now we're in the plane, so I want to use circles to group them. And again, all the triangles are always perfectly oriented. So you have a 1, 2, 3 order, and you can always collapse back to linear notation if you wanted to, right? So the notation is such that the sort of the place where you write things on the triangles, is, as you've seen in my presentation so far, is always these 3 corners of an equilateral triangle that is oriented on the page, right? So you can always project back to notation with order 1, 2, 3. So with this notation, associativity will be a ternary operation on a set that looks so that I would write like this, right? Simply like that. So some A, B, C in some set X, and this would be another element in the set X. So just to fix notation, and brackets in here will be circles. So associativity means that now it's a 5-element relation, right? So it's I put ABC as one of the corners, right? One of the entries. I encircle it just to sort of my 2-dimensional bracket in some sense. This is your planar bracket. Sorry, that was terrible. And then do some XY, right? And so if you think of associativity, binary associativity, let me just write it here. I didn't write it. I realized I didn't write binary associativity today. Binary associativity, which would be something that looks like this, you can think of it, the inspiration for these axioms is that you think of B as associating with either A or C, right? So now the idea is that we have this, instead of one single central element, we have 2 central elements, B and C. And so the idea of the axiom is that they will associate with X and Y. So they are not originally associated with A, so to speak, and then they would like to associate with X and Y. But always keeping the order. So A, B, C is 1, 2, 3. So the reason why I write them the way in which I do is so that B came first, B came before then C. So it needs to keep that overall order. So what is the next one? So I push BC to the X corner now, and I'll have something like this. I have X at the top, and I have BC here in that order because B came first in the ABC triangle, and then Y in this corner. And then, of course, it's a trio of identities, so I'll just write it down here. And so, you get the A corner, the X corner, and then BC associated. Now B comes before C, so I'll have to sort of move them in this way. So these 3, the ternary compositions of relations that I defined do not satisfy that axiom, but it's much closer to it, and it is a lot more sort of feasible for they to satisfy that kind of axiom. By the way, I did some work on this, and it turns out that in some trivial cases, these 3 associative structures reduce to, instead of one double binary associative structure, so double product of one binary actually reduces to 2 binary products, right? So the product of two binary structures, that is. But again, those were with quite strong assumptions, like one global identity for the whole thing, and which is similar to the three-group case. But it seems that this axiom is a lot closer to the sort of the ternary nature of these things, just by looking at what the formulas look like, and in fact, some of the matrix products, the cubic matrix products I introduced in the beginning, were actually satisfy this identity in one of the cases. So let me see how I'm doing with time. So right. So basically, this is what I'm at the moment. This is my current understanding of these things. So if we had a good notion of, final notion of the ternary category, or maybe a collection of notions of ternary categories, what could we do with this, and how would they help with the problems that I presented so far? So let me actually go in the same order. Let me first address cubic matrices. So as I said, cubic matrices, if you look at the products I put at the beginning, actually they essentially reproduce these ternary compositions. So actually I can zoom out a little bit now. Sorry. So actually, if you remember, I had a binary product that had sort of two indices in common, and that's what's happening in these binary compositions, two elements in common between the two relations. The ternary compositions are almost verbatim. They have one element in common, so it's one single element running through all the cubic matrices, and here it's two indices that are in common, that are sort of pairwise shared, right, between the relations. So there's an obvious analogy going on. I don't know the details of it yet, and this is where we get into the realm of what I think will be triality. So triality has been studied, has been used in some contexts, in some mathematical physics at times as well, has been used. But triality would be the sort of ternary generalization of duality. And why am I thinking of triality in this context? Well, of course, we all know that when we write a matrix like this, in conventional linear algebra, we actually know that, even though we're treating the indices just as labels, we know that actually we should be writing things like this, in physics notation. That is to say that a linear map is a 1-1 tensor, not a 0-2 tensor or a 2-0 tensor. It's a 1-1 tensor, right? So the idea here is that, well, if I have, so essentially the fact that we have two indices means that there are two kind of indices, right? The basic object being the matrix has two indices. Then we say there are contravariant indices and there are covariant indices. So now, the obvious thing to imagine is that if I have three indices, then of course I should have three kinds of indices. And this is where things get a little bit psychedelic. So I apologize in advance for the kind of symbols I'm going to be writing, but it's actually quite interesting, because the ternary products that I introduced, the ternary multiplications of matrices that I introduced, are actually very, very neat in this notation. So using physics notation where repeated indices sum over, we know that matrix multiplication here looks like this, right? So it looks like, so AB, it's expressed as AI, so it has free index I, so you sum over N, B, N, J, right? So the whole thing has free index ij. So let me just actually not use this, but be precise. So AB, apologies, there's a bit lag. Ij is this. So in this context, if I'm thinking of matrices this way, again, I'm going to enforce my triangular notation. This thing with the cubic matrices, the element ijk, both formulas that I wrote are really natural, right? Okay, so I don't want to use the summation signs. So what I do is A, B, C, same idea, right? And now I'm just doing notation. So I apologize. This is not super interesting, but the first formula was like that. So yeah, this is separated here. So this is one product. The other product is the same, but with different indices: N, B, J, M, C, K, and this is L and L, right? So I don't want to say this is the same, but this is a different product, right? Sorry, it's really lagging now. I wrote too much. Anyway, Okay, sorry, my surface is lagging a little bit. So I hope that was clear. So anyway, so the idea then would be that we have this notion of a triality among all these objects, and so in the same sense that you have V and V star in duality, in this context we will have something like V, oops, V upper star and V lower star, something in triality, right? So this is the sort of intuition that I'm having at the moment, and you know, this a triality will be this map that you know associates all these things and gives you real numbers and so on. And these things have been studied on their own right. I don't know what the connection is going to be explicitly because I still don't know exactly what the sort of the definition of a linear map in this context, or a trilinear map, or sorry, not trilinear, but a ternary linear morphism would look like yet. I mean, there's obvious paths from like linear relations and so on. And then lastly, the obvious thing to do is, well, if you have a category, well, you can just think, and with identities, you can just think of the phenomenon of invertibility and finding isomorphisms, right? So the idea would be to find the notion of ternary isomorphism or trisomorphism, if you like, and then from there just fix on a single object set of set of morphisms based on a single object, and then call that a ternary group, right? Where all the ternary morphisms are invertible, and so hopefully this will lead naturally into a notion of a sort of a ternary groupoid, right? So perhaps by and groupoid, then single object makes group. I mean, I was thinking perhaps of the name of Throop or something like that. Whatever, it's just completely speculative because I don't really have an idea. I mean, I don't know how associativity is going to work precisely. So I think I'm going to leave it at that. I think it's a good point to stop. Thanks.